Hi everyone. Welcome to KnowledgeCatch, your ultimate destination for the learning about latest advancements in technology and comprehensive learning. I'm thrilled to have you with us for today's session, where we'll be diving into the CCNA study guide. At KnowledgeCatch, we're dedicated to bringing you up-to-date and in-depth content across all tech domains. Today we're focusing on CCNA, and our goal is to equip you with the essential knowledge in just 2 hours. This is part 1 of our series, so be sure to follow along for more detailed sessions. We've meticulously organized this presentation to help you succeed in your CCNA journey. To keep things clear and structured, each slide covers approximately 10 key points. This format makes the information more digestible and easy to follow. Our content is grounded in extensive research, personal experience, and official Cisco materials, ensuring you receive a comprehensive and effective study resource. Each point has been carefully selected and reviewed to help you grasp the crucial concepts needed for the CCNA exam. We're here to support you every step of the way. So if you have any questions or need further clarification on any topic, please feel free to leave a comment. Your feedback is invaluable to us. Let's dive in and explore the world of networking together. Before beginning, let us explore the many benefits of obtaining your CCNA certification. First and foremost, CCNA is a globally recognized credential. This means that no matter where you are in the world, your certification will be acknowledged and respected, opening up numerous career opportunities in the field of networking. Next, the certification validates your networking skills. It's not just about the certificate itself, but what it represents. A comprehensive understanding of networking concepts and practical skills. This brings us to the knowledge base you will build. Studying for the CCNA ensures that you gain a deep understanding of networking fundamentals, from basic concepts to more advanced techniques. Moreover, obtaining a CCNA certification can significantly enhance your career growth potential. It demonstrates your commitment to the field and your willingness to invest in your professional development, making you a more attractive candidate for promotions and advanced roles. In terms of financial benefits, a CCNA certification often leads to higher earning potential. Employers recognize the value of certified professionals and are willing to compensate accordingly. Being a part of the Cisco community is another great advantage. You gain access to a vast network of professionals, resources, and support, which can be invaluable as you advance in your career. Additionally, staying updated with the latest technologies is crucial in the fast-paced world of networking, and the CCNA certification process ensures you remain knowledgeable about current trends and advancements. Finally, the confidence boost you receive from becoming certified cannot be overstated. It's a testament to your hard work and expertise, giving you the assurance needed to tackle challenging projects and roles. And of course, networking with industry professionals is a major benefit. Building connections can lead to new opportunities, collaborations, and career advancements. So, these are the key benefits of earning your CCNA certification. Now let's dive into the details of the CCNA exam itself, which is crucial for anyone planning to get certified. The exam code for the CCNA is 200-301. This is the current version, and it's essential to ensure you're studying the right materials for this specific exam code. The exam duration is 120 minutes, giving you a limited time to answer all questions, so time management will be key during your preparation and the actual exam. The types of questions you'll encounter include multiple choice and simulations. Multiple choice questions will test your theoretical knowledge, while simulations are designed to assess your practical skills in real-world scenarios. This combination ensures that you have both the knowledge and the hands-on ability to perform networking tasks effectively. To pass the exam, you need to score approximately 825 out of 1,000. This score might vary slightly, but aiming for this benchmark will put you in a good position to succeed. The exam is available in English and Japanese, catering to a broad audience of candidates. One of the great things about the CCNA certification is that there are no prerequisites. You don't need to have any prior certifications or specific experience to take the exam, making it accessible for beginners and those looking to switch to a networking career. Once you've earned your certification, it's valid for 3 years. During this period, you can proudly display your credential and leverage it for career opportunities. However, You'll need to recertify after 3 years to ensure your knowledge and skills remain up to date with the latest technologies and practices. Finally, you'll need to register for the exam through Pearson VUE, which is the official testing partner for Cisco certifications. Make sure to schedule your exam in advance and choose a date that gives you enough time to prepare thoroughly. These are the essential details about the CCNA exam, so keep them in mind as you start your preparation journey. Let's take a closer look at the domains covered in the CCNA exam. Understanding these areas will help you focus your study efforts and ensure you're well prepared. First, we have Network Fundamentals. This domain covers the basics of networking, including the OSI and TCP IP models, which are essential for understanding how data is transmitted across networks. Next is Network Access, which includes topics like Ethernet, VLANs, and switching. These are critical for managing and configuring local area networks, LANs. IP connectivity is another major domain. It focuses on routing protocols and IP addressing, teaching you how to route data between different networks efficiently. In the IP services domain, you'll learn about essential services like DHCP, which dynamically assigns IP addresses, NAT for translating private addresses to public ones, and NTP for time synchronization across devices. Security fundamentals is a crucial area, covering access control lists, ACLs, VPNs, and wireless security measures. This knowledge is vital for protecting network integrity and data. Automation and programmability are increasingly important in modern networking. This domain introduces you to network automation basics, helping you understand how to automate repetitive tasks and improve network efficiency. Wireless networking covers wireless standards and configurations, ensuring you can set up and manage wireless networks effectively. WAN technologies focus on wide area network technologies like MPLS, PPP, and frame relay. These technologies are used to connect geographically dispersed networks. Infrastructure services delve into SNMP and QoS. SNMP is used for network management and monitoring, while QoS ensures the performance of critical applications by managing network traffic. Finally, infrastructure maintenance covers network troubleshooting, which is essential for identifying and resolving network issues. These domains collectively provide a comprehensive understanding of networking, preparing you for various challenges you might encounter in the field. Preparing for the CCNA exam requires access to the right study resources. Here are some highly recommended resources to help you on your journey. First, the official guide from Cisco Press is an essential resource. These books are written by experts and cover all the topics in the exam syllabus thoroughly. Online courses such as those offered by the Cisco Networking Academy provide structured learning paths with interactive content and quizzes to reinforce your knowledge. Practice exams from providers like Boson and MeasureUp are invaluable. They simulate the actual exam environment, helping you get comfortable with the format and timing. Video tutorials from platforms like CBT Nuggets and Udemy offer visual and auditory learning, which can be very effective for understanding complex concepts. Joining study groups can also be beneficial. Collaborating with others who are preparing for the same exam can provide support, motivation, and different perspectives on difficult topics. Hands-on practice is crucial, and labs using tools like Packet Tracer and GNS3 allow you to configure and troubleshoot networks in a simulated environment. Forums, such as the Cisco Learning Network, are great for asking questions and finding answers from experienced professionals and fellow candidates. Flashcards are a quick review tool that can help reinforce your memory of key concepts and terms. Free Cisco webinars are also available, providing insights from experts on various networking topics. Finally, practice with simulators to get hands-on experience with different scenarios you might encounter in the exam. Utilizing these resources will help you build a solid foundation and boost your confidence as you prepare for the CCNA exam. Understanding the OSI model is fundamental for anyone studying networking, and it's a core part of the CCNA exam. The OSI model is a conceptual framework used to understand network interactions in 7 distinct layers. Layer 1 is the physical layer, which deals with the physical connection between devices. This includes cables, hubs, and other physical transmission mediums. Layer 2 is the data link layer, responsible for node-to-node data transfer. It includes MAC addresses and devices like switches, which manage local network traffic. Layer 3 is the network layer. This layer handles the routing of data packets across networks and includes IP addresses and routers. Layer 4 is the transport layer, which ensures end-to-end communication and data integrity between devices. It includes protocols like TCP and UDP. Layer 5 is the session layer. It manages and controls the connections between computers, ensuring that the sessions remain open until communication is complete. Layer 6 is the presentation layer, which translates data between the application layer and the network format. This includes data encryption and translation. Layer 7 is the application layer, which provides network services directly to the user applications. This includes services like email, file transfer, and web browsing. The function of the OSI model is to standardize network communication, ensuring interoperability between different systems and technologies. It's the foundation of networking, providing a universal set of guidelines that helps different networks and devices work together seamlessly. When comparing the OSI model to the TCP/IP model, the OSI model is more detailed with its 7 layers, while the TCP/IP model has 4 layers, combining some of the OSI layers. Understanding both models is crucial as they are used in different contexts within the field of networking. The OSI model remains a fundamental concept that underpins all networking knowledge, making it an essential topic for the CCNA exam. Now let's take a look at the TCP/IP model, another crucial framework in networking. The TCP/IP model has 4 layers, which correspond to specific functions and protocols used in network communication. Layer 1 is the network interface layer, which includes hardware and technologies like Ethernet and Wi-Fi. This layer is responsible for the physical connection and data link between devices. Layer 2 is the Internet layer. It deals with logical addressing and routing, using protocols like IP and ICMP to move packets across networks. Layer 3 is the transport layer, ensuring reliable data transfer between devices. This layer includes the TCP and UDP protocols, which manage data segmentation and reassembly. Layer 4 is the application layer, providing network services to applications. This includes protocols like HTTP, FTP, and SMTP, which facilitate web browsing, file transfers, and email communication. Comparing the OSI and TCP/IP models, the OSI model is more granular with 7 layers, while the TCP/IP model consolidates these functions into 4 layers. Both models are essential for understanding different aspects of networking. The TCP/IP model functions as the standard protocol suite for Internet communication. It's the foundation of modern networking, ensuring that different systems can communicate effectively over the Internet. The development of the TCP/IP model originated with DARPA, the Defense Advanced Research Projects Agency, which laid the groundwork for the Internet as we know it today. One of the key strengths of the TCP/IP model is its adaptability. It supports multiple protocols and technologies, making it versatile for various networking environments. Understanding the TCP/IP model is essential for modern networking. It's the basis for most networking operations, particularly those involving Internet communication. This model is fundamental for anyone pursuing a career in networking and is a critical component of the CCNA exam. Understanding networking devices is crucial for managing and configuring networks. Let's go over the key devices you'll need to know for the CCNA exam. First, the router. Routers are essential for directing data packets between different networks. They use routing tables and protocols to determine the best path for data to travel. Next is the switch. Switches connect devices within a local area network, LAN. They use MAC addresses to forward data only to the intended recipient, improving network efficiency and security. Firewalls are critical for network security. They act as barriers, controlling incoming and outgoing traffic based on predetermined security rules. Firewalls can be hardware-based, software-based, or a combination of both. Hubs are basic connectivity devices that connect multiple Ethernet devices, making them act as a single network segment. However, unlike switches, hubs do not filter data and can lead to network inefficiencies. Bridges are used to connect different network segments, ensuring that data is properly routed between them. They help manage traffic and reduce collisions in a network. Access points provide wireless connectivity, allowing devices to connect to the network wirelessly. They are crucial for extending network coverage and supporting mobile devices. Modems modulate and demodulate signals for data transmission over telephone lines or cable systems. They are used to connect networks to Internet Service Providers, ISPs. Repeaters are used to extend the range of signals by amplifying them, allowing data to travel longer distances without degradation. Gateways connect different networks and protocols, enabling communication between systems that use different technologies. They act as translators between different network architectures. Each of these devices plays a vital role in network functionality, ensuring data can be transmitted, received, and processed efficiently and securely. Understanding the function and configuration of these networking devices is essential for managing networks effectively and is a significant part of the CCNA curriculum. IP addressing is a fundamental aspect of networking, enabling devices to identify and communicate with each other. IPv4 is the most widely used IP addressing system, utilizing 32-bit addresses. This format allows for approximately 4.3 billion unique addresses. IPv6 was developed to address the limitations of IPv4, offering 128-bit addresses. This vastly increases the number of available addresses, supporting the growing number of Internet-connected devices. Public IP addresses are globally unique and assigned by ISPs. They are used for devices that need to be accessible from the Internet. Private IP addresses are used within internal networks. These addresses are not routable on the Internet, allowing organizations to reuse the same address ranges without conflicts. The subnet mask is used to divide an IP address into network and host portions. It helps in determining the network segment a device belongs to, and is crucial for subnetting. CIDR notation, which stands for classless interdomain routing, is a method for specifying IP addresses and their associated routing prefix. It's written as an IP address followed by a slash and the prefix length, such as 192.168.0/24. DHCP, or Dynamic Host Configuration Protocol, automates the assignment of IP addresses to devices on a network. This simplifies IP management, especially in large networks. Static IP addresses are manually assigned to devices and remain constant. They are often used for servers and devices that require a consistent IP address. Classful addressing divides the IP address space into 5 classes, A, B, C, D, each with a different range of addresses and subnet masks. This method is mostly historical, as CIDR has largely replaced it for more efficient IP address allocation. Understanding IP addressing is critical for network communication. It ensures that data packets are correctly routed to their destinations, allowing devices to communicate effectively across both local and wide area networks. Mastering these concepts is essential for the CCNA exam and for anyone looking to work in networking. Subnetting is a crucial technique in networking that allows for efficient utilization of IP addresses. The primary purpose of subnetting is to divide a large network into smaller, more manageable subnetworks or subnets. This not only helps in efficient IP address utilization, but also improves network performance and security. A subnet mask is used to determine the network and host portions of an IP address. It plays a key role in defining the boundaries of each subnet. The formula for calculating the number of subnets and hosts is 2 to the power of n2, where n is the number of bits borrowed for subnetting. This formula helps in determining the possible number of subnets and hosts within each subnet. For example, a /24 subnet mask means that the first 24 bits of the IP address are used for the network portion, leaving the remaining bits for host addresses. VLSM, or variable length subnet masking, allows for more flexible and efficient IP address allocation by using different subnet masks within the same network. This technique helps in optimizing the use of IP addresses based on the size of each subnet. Practicing subnetting exercises is essential for mastering this concept. It helps in understanding how to apply subnetting in real-world scenarios. One of the major benefits of subnetting is the reduction of broadcast domains. By dividing a large network into smaller subnets, the impact of broadcast traffic is minimized, leading to improved network performance. CIDR, or classless interdomain routing, further enhances subnetting by allowing for more efficient IP address allocation and aggregation. It eliminates the limitations of classful addressing and provides greater flexibility. Using subnet calculators can aid in quickly determining subnet boundaries, the number of subnets, and the number of hosts per subnet. These tools are invaluable for network planning and design. Overall, subnetting enhances network design by allowing for better organization, improved performance, and efficient IP address management. Mastering subnetting is crucial for anyone pursuing a career in networking and is a significant part of the CCNA curriculum. Ethernet is a fundamental technology used for local area networks, LANs, and understanding its basics is essential for networking professionals. Ethernet is defined as a LAN technology that facilitates communication between devices within a local network. It's standardized by IEEE 802.3, which defines the physical and data link layer specifications. Ethernet frames are the units of data transmission in Ethernet networks. Each frame contains a header, payload, and trailer. The header includes the source and destination MAC addresses, which are unique hardware identifiers for each network interface card, NIC. Ethernet speeds have evolved significantly over the years, ranging from 10 megabits per second to 100 gigabits per second. This evolution allows Ethernet to support a wide range of applications, from simple file sharing to high bandwidth tasks like video streaming and data center operations. Duplex modes in Ethernet can be either half duplex or full duplex. Half duplex allows data transmission in one direction at a time, while full duplex supports simultaneous bidirectional communication, improving network efficiency. Ethernet can use different media types, including copper cables and fiber optics. Copper cables are commonly used for shorter distances, while fiber optics are preferred for longer distances and higher speeds due to their superior performance and lower susceptibility to interference. The topology of Ethernet networks can be bus or star. In a bus topology, all devices share a single communication line, while in a star topology, each device is connected to a central hub or switch. Star topology is more common in modern networks due to its reliability and ease of troubleshooting. Understanding the concepts of collision and broadcast domains is also important. A collision domain is a network segment where data packets can collide, leading to network inefficiencies. Ethernet switches help reduce collision domains by segmenting the network. A broadcast domain is a network segment where a broadcast frame is forwarded to all devices. Subnetting and VLANs are used to manage and reduce the size of broadcast domains. Overall, Ethernet forms the backbone of most LANs, and mastering its basics is crucial for networking professionals. It's a key component of the CCNA curriculum, and understanding it will help you design and manage efficient network infrastructures. Switching concepts are fundamental to understanding how data moves within a network. Switches forward data based on MAC addresses, creating a more efficient and secure network environment. Unlike hubs, switches only send data to the intended recipient. Virtual LANs or VLANs allow network segmentation, improving security and reducing congestion. Each VLAN operates as a separate network. Trunking enables multiple VLANs to be transmitted over a single physical link using the 802.1q protocol. This is essential for maintaining VLANs across multiple switches. The spanning tree protocol (STP) prevents network loops, which can cause significant disruptions. STP ensures there is a single active path between switches. Switch ports can be configured as access ports, which connect end devices, or trunk ports, which connect switches and carry VLAN traffic. The MAC address table on a switch learns and stores MAC addresses, ensuring data is forwarded to the correct destination. This table is dynamic and updates as devices connect and disconnect. VTP, or VLAN trunking protocol, helps manage VLAN configurations across a network of switches, ensuring consistency. Switch stacking allows multiple switches to operate as a single unit, simplifying management and improving performance. Power over Ethernet (PoE) provides power to devices like IP phones and cameras through the Ethernet cable, eliminating the need for separate power supplies. Understanding these concepts is essential for configuring and managing switches in a network, making it a key area for the CCNA exam. Spanning Tree Protocol (STP) is crucial for preventing network loops in Ethernet networks. The primary purpose of STP is to ensure a loop-free topology in networks with redundant paths. Without STP, loops can cause broadcast storms and network failures. The root bridge is the central reference point in an STP-enabled network. All path calculations are made with reference to the root bridge. Bridge Protocol Data Units (BPDUs) are used by switches to share information about network topology and ensure all switches have a consistent view of the network. Ports in STP can be in different states: blocking, listening, learning, forwarding, and disabled. These states help manage the network topology changes and prevent loops. Each port also has a specific role, such as root port, designated port, or blocking port. These roles determine how a port participates in forwarding traffic. STP uses timers like hello time, forward delay, and max age to control the timing of topology changes and convergence. Rapid Spanning Tree Protocol (RSTP) is an enhancement to STP that provides faster convergence times. It's defined in the IEEE 802.1W standard. Per VLAN Spanning Tree Plus, PVST Plus, allows for a separate spanning tree instance for each VLAN, providing greater flexibility and efficiency. BPDU Guard is a security feature that disables a port if it receives a BPDU, protecting the network from potential misconfigurations. Understanding STP and its mechanisms is essential for managing complex network topologies and is a key topic in the CCNA exam. Ether channel, also known as link aggregation, is a technique used to increase bandwidth and provide redundancy between switches. The primary purpose of Ether channel is to combine multiple physical links into a single logical link, enhancing bandwidth and providing fault tolerance. Protocols used in Ether channel include PAGP, Port Aggregation Protocol, and LACP, Link Aggregation Control Protocol. These protocols help in the automatic creation and management of Ether channel links. Ether channel can be configured using static methods or dynamic protocols like PAGP and LACP. Static configuration requires manual setup, while dynamic protocols negotiate the links automatically. Load balancing in Ether channel distributes traffic across the available links based on criteria such as source/destination MAC addresses, IP addresses, or Layer 4 ports. Ether channel supports a maximum number of links, typically up to 8, providing substantial bandwidth and redundancy. Compatibility between devices and links is crucial for Ether channel to function correctly. All participating ports must have the same settings. Troubleshooting Ether channel involves checking for configuration consistency, proper protocol settings, and verifying the status of individual links. The benefits of Ether channel include increased bandwidth, improved redundancy, and simplified management. Common use cases for Ether channel include connecting switches, servers, and other network devices that require high availability and bandwidth. Mastering Ether channel is important for network design and optimization, making it a critical topic for the CCNA exam. LAN design involves creating a network architecture that ensures high performance, scalability, and security. The hierarchical model is a common design framework, consisting of 3 layers: core, distribution, and access. The core layer acts as the high-speed backbone of the network, ensuring rapid data transport across the network. The distribution layer provides policy-based connectivity, aggregating data from the access layer and forwarding it to the core layer. It also handles routing and access control policies. The access layer connects end devices to the network, including computers, printers, and IP phones. This layer also implements security measures like port security and VLANs. Redundancy is critical for ensuring network availability. Implementing redundant links and devices helps prevent single points of failure. Scalability is another key aspect, ensuring the network can grow and accommodate additional devices and users without significant reconfiguration. Performance optimization involves using technologies like Ether channel, QoS, and efficient routing protocols to ensure fast and reliable network operation. Security measures such as ACLs, firewalls, and secure VLAN configurations protect the network from threats and unauthorized access. Management and administration are simplified through the use of network management tools, standardized configurations, and automated processes. Best practices in LAN design include proper planning, regular updates, and adhering to industry standards. Understanding LAN design principles is essential for creating efficient and reliable networks, making it a crucial part of the CCNA exam. Routing is the process of selecting paths in a network along which to send data packets. Static routing involves manually configuring routes on routers. This method is straightforward but lacks scalability and adaptability to network changes. Dynamic routing uses protocols to automatically adjust routes based on network conditions. This approach is more flexible and scalable. A routing table is a database in routers that stores route information. It includes the destination network, the next hop, and metrics for route selection. Metrics are criteria used by routing protocols to determine the best path to a destination. Common metrics include hop count, bandwidth, delay, and cost. Administrative distance is a value that indicates the trustworthiness of a route. Lower values indicate more preferred routes. Common routing protocols include RIP, EIGRP, OSPF, and BGP. Each protocol has its own characteristics, advantages, and use cases. Convergence is the process by which all routers in the network agree on the network topology. Faster convergence is desirable for network stability and performance. A default route is a catch-all route, used when no specific route to a destination is found in the routing table. It's often referred to as the gateway of last resort. Load balancing distributes traffic across multiple paths, improving network performance and redundancy. This can be achieved using equal cost or unequal cost load balancing. Understanding routing basics is essential for managing and troubleshooting networks, making it a key topic in the CCNA exam. Routing protocols are essential for dynamic routing in networks. Let's explore some common protocols. RIP, or Routing Information Protocol, is a distance vector protocol that uses hop count as its metric. It's simple but less efficient for large networks due to its limited hop count. IGRP, or Enhanced Interior Gateway Routing Protocol, is a hybrid protocol that combines features of both distance vector and link state protocols. It uses composite metrics, including bandwidth and delay, for route selection. OSPF, or Open Shortest Path First, is a link state protocol that uses the Dijkstra algorithm to calculate the shortest path. It's highly efficient and scalable, making it suitable for large and complex networks. BGP, or Border Gateway Protocol, is a path vector protocol used for routing between autonomous systems on the Internet. It uses a variety of attributes for path selection and is essential for Internet routing. Metric calculation varies by protocol. For example, RIP uses hop count, OSPF uses cost based on link bandwidth, and EIGRP uses a composite metric of bandwidth and delay. Route summarization is the process of combining multiple routes into a single, more efficient route. This reduces the size of routing tables and improves network performance. VLSM, or Variable Length Subnet Masking, is supported by most modern routing protocols. It allows for more efficient IP address allocation by using different subnet masks within the same network. Authentication in routing protocols ensures that routing updates are exchanged securely. Protocols like OSPF and EIGRP support authentication mechanisms to prevent unauthorized updates. Route redistribution allows different routing protocols to share routes. This is useful in networks where multiple routing protocols are used. Scalability is an important consideration when choosing a routing protocol. Protocols like OSPF and BGP are highly scalable, making them suitable for large networks. Understanding these routing protocols is crucial for managing dynamic routing in networks, making it a key topic for the CCNA exam. Inter-VLAN routing is a technique used to route traffic between different VLANs in a network. The traditional method of inter-VLAN routing is known as router on a stick. This setup involves a single router interface connected to a switch, with multiple subinterfaces configured for each VLAN. Each subinterface on the router is assigned an IP address and VLAN tag, allowing it to route traffic between VLANs. This method is simple but can become a bottleneck as traffic increases. VLAN tagging uses the 802.1q protocol to insert VLAN tags into Ethernet frames. This allows frames to carry VLAN information as they travel across trunk links. Switch virtual interfaces, SVIs, are another method for inter-VLAN routing. SVIs are logical interfaces configured on a Layer 3 switch. Each SVI is assigned an IP address and associated with a VLAN. SVIs provide improved performance and scalability compared to router on a stick, as they eliminate the need for a separate router and reduce the traffic bottleneck. The configuration of SVIs involves creating VLANs, assigning IP addresses to the SVIs, and enabling IP routing on the switch. Inter-VLAN routing provides several advantages, including improved network segmentation and better traffic management. It allows different VLANs to communicate securely and efficiently. Performance considerations include ensuring that the switch or router used for inter-VLAN routing can handle the traffic load without becoming a bottleneck. Security is also important in inter-VLAN routing. Access control lists, ACLs, can be used to control traffic between VLANs, ensuring that only authorized traffic is allowed. Troubleshooting inter-VLAN routing issues involves checking VLAN configurations, verifying IP address assignments, and ensuring proper VLAN tagging on trunk links. Understanding inter-VLAN routing is essential for managing and securing VLANs in a network, making it a key topic for the CCNA exam. Route summarization is a technique used to reduce the size of routing tables and improve network efficiency. Route summarization involves combining multiple specific routes into a single summary route. This reduces the number of entries in the routing table and simplifies routing. Manual summarization is performed by network administrators who configure summary routes on routers. This method provides control over which routes are summarized. Automatic summarization is performed by some routing protocols, such as RIP and IGRP. These protocols automatically generate summary routes based on network boundaries. RIP, or Routing Information Protocol, performs automatic summarization by default. However, this feature can be disabled if manual control is desired. EIGRP, or Enhanced Interior Gateway Routing Protocol, supports both automatic and manual summarization. Network administrators can configure summary routes at any point in the network. OSPF, or Open Shortest Path First, performs summarization at the area boundaries. Area-based summarization reduces the amount of routing information exchanged between areas. BGP, or Border Gateway Protocol, uses route aggregation to summarize routes. This is essential for reducing the size of the global routing table on the Internet. Route summarization offers several benefits, including reduced routing table size, improved routing efficiency, and decreased bandwidth usage for routing updates. However, summarization can also have limitations. Incorrect summarization can lead to suboptimal routing, where traffic takes longer paths due to inaccurate summary routes. Best practices for route summarization include summarizing routes at appropriate points in the network, regularly reviewing summary routes, and using tools to validate summarization. Understanding route summarization is essential for managing large and complex networks, making it a key topic for the CCNA exam. Access control lists, ACLs, are a fundamental security feature used to control traffic flow and enforce policies in a network. The primary purpose of ACLs is to filter traffic based on various criteria, such as source and destination IP addresses, protocols, and port numbers. This helps protect the network from unauthorized access and potential threats. There are two main types of ACLs: standard and extended. Standard ACLs filter traffic based solely on source IP addresses, while extended ACLs provide more granular control by filtering traffic based on source and destination IP addresses, protocols, and port numbers. Standard ACLs use a numbering range of 1 to 99 and 1300 to 1999, while extended ACLs use a range of 100 to 199 and 2000 to 2699. These numbers help identify and manage different ACLs in the configuration. The placement of ACLs is crucial for their effectiveness. Best practices suggest placing standard ACLs close to the destination and extended ACLs close to the source. This helps optimize network performance and minimize unnecessary traffic filtering. Wildcard masks are used in ACLs to specify IP address ranges. They work by indicating which bits of the IP address should be matched, and which should be ignored. One important aspect of ACLs is the implicit deny rule. At the end of every ACL, there is an implicit deny statement that blocks all traffic not explicitly permitted. This ensures that any unspecified traffic is denied by default. Configuring ACLs involves defining the ACL entries and applying them to the appropriate interfaces in the network. This process requires careful planning and testing to avoid unintended traffic disruptions. Troubleshooting ACLs involves verifying the ACL configuration, checking the order of entries, and ensuring that the ACLs are applied correctly to the interfaces. Understanding ACLs is essential for network security and traffic management, making it a key topic for the CCNA exam. Dynamic Host Configuration Protocol (DHCP) is a network protocol used to automatically assign IP addresses and other configuration parameters to devices on a network. DHCP simplifies IP address management by dynamically assigning IP addresses to devices as they connect to the network. This eliminates the need for manual IP address configuration and reduces the risk of IP conflicts. The DHCP process involves 4 main steps, known as DORA: discover, offer, request, and acknowledge. These steps ensure that devices receive the necessary IP configuration. A DHCP server is responsible for managing the IP address pool and allocating addresses to clients. It can also provide other configuration parameters, such as the default gateway, DNS servers, and subnet mask. Clients send a DHCP discover message to locate available DHCP servers. The server responds with a DHCP offer, proposing an IP address and other configuration parameters. The client then sends a DHCP request message, indicating its acceptance of the offered IP address. The server finalizes the process with a DHCP acknowledge message, confirming the assignment. Lease time determines how long an IP address is assigned to a device. When the lease expires, the device must renew the lease or request a new IP address. DHCP scopes define the range of IP addresses available for assignment. Each scope can include additional options, such as default gateways and DNS servers. Reservations allow specific devices to receive the same IP address every time they connect to the network. This is useful for devices that require a consistent IP address, such as printers and servers. DHCP options provide additional configuration settings, such as DNS servers, domain names, and time servers. These options can be included in the DHCP offer message. Security considerations for DHCP include preventing rogue DHCP servers, which can disrupt network operations. This can be achieved through DHCP snooping and other security measures. Understanding DHCP is essential for efficient network management and is a key topic in the CCNA exam. Network Address Translation (NAT) is a technique used to modify network address information in IP packet headers while in transit, allowing multiple devices on a local network to share a single public IP address. The primary purpose of NAT is to conserve public IP addresses by allowing private IP addresses within a local network to communicate with external networks using a single public IP address. There are 3 main types of NAT: static NAT, dynamic NAT, and port address translation (PAT). Static NAT involves a one-to-one mapping between a private IP address and a public IP address. This type of NAT is often used for servers that need to be accessible from the outside. Dynamic NAT uses a pool of public IP addresses and maps them to private IP addresses on a first-come, first-served basis. This type of NAT is more flexible, but requires a sufficient number of public IP addresses. PAT, also known as NAT overload, maps multiple private IP addresses to a single public IP address by using different port numbers. This is the most common type of NAT used in home and small business networks. NAT configuration involves defining the translation rules and applying them to the appropriate interfaces. This process includes specifying the inside and outside interfaces and configuring the address mappings. NAT offers several benefits, including IP address conservation, increased security by hiding internal IP addresses, and the ability to connect multiple devices to the internet using a single public IP address. However, NAT also has drawbacks. It can introduce latency and complexity, and certain applications and protocols may not function properly through NAT without additional configuration. Troubleshooting NAT involves verifying the configuration, checking address mappings, and ensuring that NAT rules are correctly applied to the interfaces. Understanding NAT is essential for managing IP address space and enabling communication between private networks and the public internet, making it a key topic for the CCNA exam. Network Time Protocol (NTP) is a protocol used to synchronize the clocks of network devices to ensure accurate timekeeping across the network. The importance of accurate time synchronization cannot be overstated. It is essential for logging events, coordinating tasks, and ensuring the proper functioning of time-sensitive applications. NTP operates in a hierarchical system of time sources, known as strata. Stratum 0 devices, such as atomic clocks and GPS receivers, provide the most accurate time. Stratum 1 devices synchronize directly with Stratum 0 devices, and so on. NTP servers provide time synchronization services to clients on the network. Clients synchronize their clocks with the NTP server to maintain accurate time. Server configuration involves setting up the NTP server to provide time services. This includes specifying the time sources and configuring the server's stratum level. Client configuration involves setting up network devices to synchronize their clocks with an NTP server. This ensures that all devices on the network have consistent and accurate time. Authentication in NTP provides security by ensuring that time synchronization messages are not tampered with. This is important for maintaining the integrity of time-sensitive operations. Peer mode allows devices to synchronize their clocks with each other, providing redundancy and improving the accuracy of timekeeping across the network. Broadcast mode simplifies client configuration by allowing the NTP server to broadcast time updates to all devices on the network. This is useful for networks with many clients. NTP pools are collections of publicly available NTP servers. These servers provide reliable and accurate time synchronization services to devices worldwide. Troubleshooting NTP issues involves verifying the configuration, checking the synchronization status, and ensuring that the NTP messages are being transmitted correctly. Understanding NTP is essential for maintaining accurate timekeeping and ensuring the proper functioning of network operations, making it a key topic for the CCNA exam. Simple Network Management Protocol, SNMP, is a protocol used for monitoring and managing network devices. SNMP operates by exchanging management information between network devices. It allows network administrators to monitor network performance, detect faults, and configure devices remotely. The key components of SNMP include the SNMP Manager, SNMP Agents, and Management Information Bases, MIBs. The SNMP Manager is a software application that collects and analyzes data from network devices. It communicates with SNMP agents to gather information and send configuration commands. SNMP agents are software components running on network devices. They collect data about the device's performance and status and respond to requests from the SNMP Manager. MIBs are databases that define the structure of the management data on a device. They contain a collection of managed objects, each identified by a unique object identifier, OID. SNMP versions include SNMPv1, SNMPv2c, and SNMPv3. SNMPv3 introduces security enhancements, such as encryption and authentication, to protect management information. Community strings are used in SNMPv1 and SNMPv2c to control access to the SNMP data. They function like passwords with read-only and read-write access levels. Traps are notifications sent by SNMP agents to the SNMP Manager when specific events occur. They help network administrators respond to issues in real time. Polling involves the SNMP Manager regularly querying devices for information. This helps maintain an up-to-date view of the network's status and performance. OIDs are unique identifiers for managed objects in the MIB. They provide a standardized way to access specific data on network devices. Security in SNMP is crucial to protect management data from unauthorized access and tampering. SNMPv3 offers features like encryption and authentication to enhance security. Understanding SNMP is essential for effective network management and monitoring. making it a key topic for the CCNA exam. Quality of Service (QoS) is a set of techniques used to manage and prioritize network traffic, ensuring the performance of critical applications. The importance of QoS lies in its ability to ensure that high-priority traffic, such as voice and video, receives the necessary bandwidth and low latency for optimal performance. QoS involves several key components, including classification, marking, queuing, shaping, and policing. Classification identifies and categorizes different types of traffic based on criteria such as IP addresses, protocols, and application types. This step is crucial for applying specific QoS policies to different traffic classes. Marking assigns QoS values, such as Differentiated Services Code Point (DHCP) or Class of Service (COS), to packets. These markings indicate the priority level of the traffic as it traverses the network. Queuing manages packet queues based on their QoS markings. Different queuing algorithms such as first-in first-out (FIFO) and weighted fair queuing (WFQ) determine the order in which packets are transmitted. Shaping smooths traffic bursts by delaying packets to ensure a consistent flow of traffic. This helps prevent network congestion and ensures that high-priority traffic receives the necessary bandwidth. Policing enforces bandwidth limits by discarding or remarking packets that exceed the specified rate. This helps maintain network performance by preventing excessive traffic from overwhelming the network. Trust boundaries define the points in the network where QoS markings are trusted or modified. Maintaining trust boundaries ensures that QoS policies are consistently applied across the network. Configuring QoS involves defining and applying QoS policies to network devices. This includes setting classification rules, marking packets, and configuring queuing and shaping mechanisms. Understanding QoS is essential for managing network performance and ensuring the quality of critical applications, making it a key topic for the CCNA exam. WAN concepts are crucial for understanding how to connect geographically dispersed networks. A WAN, or wide area network, connects networks that are spread across large distances. This is essential for businesses with multiple locations or remote branches. Several technologies are used to implement WANs, including MPLS, Frame Relay (PPP), and Metro Ethernet. MPLS, or multi-protocol label switching, is a high-performance technique that directs data through the network based on short path labels rather than long network addresses. This improves speed and efficiency. Frame Relay is a packet switch technology that uses virtual circuits to connect multiple sites. It's cost-effective and scalable, but has largely been replaced by more modern technologies. PPP, or point-to-point protocol, provides a direct connection between two network nodes. It supports authentication, encryption, and compression. Metro Ethernet extends Ethernet technology to the metropolitan area network (MAN), providing high-speed connectivity over large geographic areas. Leased lines such as T1 and E1 circuits offer dedicated, point-to-point connections between sites. They provide consistent bandwidth but can be expensive. Circuit switching, used in technologies like ISDN, establishes a dedicated path for the duration of a communication session. This is reliable but less efficient than packet switching. Packet switching, used in technologies like Frame Relay and MPLS, allows data to be sent in packets over shared networks. This is more efficient and cost-effective. VPNs, or virtual private networks, provide secure connections over public networks. They use encryption and tunneling protocols to ensure data privacy and integrity. DSL, or digital subscriber line, provides high-speed internet access over telephone lines. It's widely available, but can be affected by distance from the provider's central office. Cable broadband uses the same infrastructure as cable TV to provide high-speed internet access. It offers higher speeds than DSL, but can be affected by network congestion. Satellite connectivity is used for remote areas where traditional wired connections are not feasible. It provides wide coverage but can have higher latency. Cellular networks, including 3G, 4G, and 5G, offer mobile broadband connectivity. They are essential for mobile devices and remote locations. Understanding WAN concepts is crucial for designing and managing wide area networks, making it a key topic for the CCNA exam.